I'll be discussing the data path subcircuit. In subsequent ones, I will discuss the control, then the ACC in. So we'll take a deep dive to see what this subcircuit consists of, the data path subcircuit. So here it is. As you can see, let me get the full picture of what the data path subcircuit looks like. So here you can see the two stacks. It has two stacks, an ALU and a multiplexer here. So, and this little subcircuit which is used to generate this great signal we discussed earlier. So I'll just take a brief tour of each of these subcircuits just quickly. First, let's see what is contained within the ALU. So this has always been the basic design of every ALU. You have a big multiplexer that does several functions, and then you have one output and two inputs, and then you have your LU in, or your LU selector, which picks which particular operation you want to perform. So I'll just briefly explain this LU and how it operates. First of all, I arrange all the operations according to their priority. So remember the great signal I talked about. This is where the logic comes in. The division has the highest value in the multiplexer, or no, the NOT gate before the division. So in a case you are designing something similar, it's up to you to determine which of the operation will have the highest priority. So I have here division as the highest priority here because it has the highest value in the multiplexer. 0 is your OR, 1 is your OR, 0 is your 2, AND is your 3, shift left, shift right, plus, minus, multiplication, and the rest of them. So in a situation you have a computation like 2 plus 2 divided by 3. So it compares the plus there and the division, and since the division is higher, it's going to bring another more equation in. So this is where the priority decision is taken depending on which selection you give in. So if you put division, that means division is higher than all of them, and it will be given the highest priority during computation. I will explain more on this when we'll be talking about the great signal and how it's being generated. So here again you have your A, B, and C signal. So these three signal A in, B in, and C in signals are used to unlock this multiplexer to take new input. So during computation, assuming you have your A in signal on, this input in goes into the A register. If you have your B in signal on, this input in goes into your B register. So, and if you have your LU, the C in on, this LU in goes in here. And whenever it goes in, only bit 3 down to 0 is being selected. Bit 3 down to 0 is what is used to control the multiplexer, not the whole of the 16 bits that comes in. So you only take them. And after every computation, you can see that I gave the MSB is always given as 0. The MSB, you always add a 0 to the. So the major reason for adding that particular 0 to the MSB is just to distinguish between a figure and an operator. All the operator will always, the MSB is always 1, and all the numbers will be operating on, the MSB is always 0. So whenever you get to LU out, so in case you have a negative number that usually starts with 0, 0, 0, that usually starts with 1, 1, 1, it won't affect the MSB. The MSB will always be 0, indicating that it's a number, not a figure. That is, in a case you have an overflow or maybe a negative number, and that also occurs here during the selection. The MSB is always omitted because the MSB is more like a sign bit that differentiates between an operation and a number. So here you can see is only 3 down to 0 is used to work on the multiplexer. And remember about the priority. The higher the value, the higher the priority. When I'll be explaining the greater than signal, I will show you where this particular analogy is used. So this is basically how this area is used, and all this A, B, and C signal that is used to open all those multiplexers are coming from the control signal. So when we'll be talking about the control signal, I'll show you how they are all being generated. A, B, and C signal, how they are being generated. Now let's talk about this multiplexer again. So okay, before that, you also see that for this inputting, for the input going to the register A and B, they are coming from the first stack. You can see where they went in from the first stack, because that is where the figures are stored. Whereas for the LU in, is coming from the second stack, which stores the operators. The arithmetic operators is coming from stack 2. So that is how the numbers goes to stack A and the figures, the operators, go to stack B. So then again, let me show you how this greater than is being generated. So that is how my algorithm works. So what it does is, first of all, a signal pops out the last 2 operators from the stack. The first one goes in here and is stored. The second one goes in here and is likewise. So let me remove the marker, sorry. Depending on this signal E, this signal E is used to turn on this register here, and immediately after it, this one comes on also. So whenever the signal E comes on, which is also coming from the control, this multiplexer stores the popped out data from the stack. Then the next signal stores here. Let me show you. E is used to turn on this register here. Then watch this multiplexer is coming from C. So the same signal C that turns on the LU operator is the same that turns on this register too. So whenever these two has accumulated data from stack B, which are the operators, that is after port B signal has been turned on twice to pop out the last 2 operators, this comparator compares the 2 of them and generates this signal. This signal is then sent back to the control, and at the control, the decision is made whether to go on with the calculation or whether to add more inputs. When you go through the Velo code, all these things are more highlighted and explained there. So, and to show which one is greater, remember in the ALU, the higher the value, the higher the priority. So division comes almost highest in all of them. So that is how this greater than is generated, and it will be sent to the control signal to determine what value next to follow. So let's talk about this multiplexer here. So this multiplexer they are actually 4 inputs with a control signal here, and this control signal is also coming from the control circuit sub-circuit. So it makes a decision to determine which data to be sent to the stack. They have different data that can be sent to the stack. So it makes choice from these 4 different signals and makes a particular output. Let's go back to the data part, so I'll show you how the 4 of them are being selected. So first of all, the first one is your data in. So this one is your input data coming from the ACC in sub-circuit. That is, whenever this deselect is equal to 0, that means you are reading, you are getting input from your data in, that is your ACC in, and the output goes back into the two stacks. That is the output of this multiplexer, the mux subcircuit. So this mux subcircuit selects which data to be sent back to the stack. First, if it's 0, 0, it takes your data in. If it's 1, it takes the LDO output. Let's trace it, and you see it's coming from the LDO output. If it's 3, it's coming from here. It's coming from the data being stored in this first register, and if it's 2, then if it's 3, it's coming from this second register here. So when we will be discussing the control, you will now see how this select signal is being generated to choose which of the data inputs that is being needed. Then also let's talk finally about the stack, the simple design of a stack. And the stack is the main idea behind the computation. So it consists of your stack memory. This is a stack register here that has from address 0 to address 1F. This is your stack pointer, and this is your stack register. This is your push signal, your pop signal. This is your data in, and this is your data out. So let me remove this. Okay, so whenever you decide to push, that is, want to put a data in, you can watch where it comes here. Whenever the push is on, once a high is sent to the write enable. So for you to push means you want to write, and the write enable comes on. If you are popping, you are not able to write. That is what this particular multiplexer here does. It chooses when to turn on the write enable of this RAM. So then again, you have your stack pointer, which is what generates the actual address that goes in to the stack memory. And your stack pointer is stored within this register, your stack register, which is controlled with the normal clock and reset. So whenever you want to push, it increments by 1. The stack pointer increments by 1, and whenever you want to decrement, the stack pointer decrements by 1. That is, you have this series of memory, all of them here. So whenever you choose push, it comes to the next memory and push. If you choose push here, it goes here and push it in here. You push again, it comes here and push it in. You push again, it comes down here. From here to here to here. Then it continues like that, going down till here. So if you are going to pop, the same thing, it starts going backwards, giving you an output backwards, going from one address down 1 bit lower than the previous address. So that is how they're able to go up and down. It goes up when it's trying to in, and down when it's trying to remove. So that is it for the stack. It's just a very simple circuit. So this is it, the external of it. So that is how all of them makes up this data path subcircuit. So but when you go through the code, you'll be able to understand it more. I think what I did is just to give an overview of how the data path works. Please go to my site to get the code, go through it. It's a very simple and easy circuit, but it does a very huge complex math. Minus, it is not able to operate on brackets. So that is how this data path works. Please like, share and subscribe to my channel. Thank you so much.